4.9 is redox reactions. So first question that we have here is asking us to identify oxidation states in these chemical equations. So there are a set of rules for oxidation states that we're going to use in order to determine what they are for each of these compounds. So when you have a pure element in its standard state, so that would be the state that it's in at 25 degrees Celsius. So sodium is a metal, a solid, so that's going to have an oxidation state of 0. Same thing with the chlorine gas, so it's in its standard state. And then for our products here, these are both monatomic ions. So the charge on a monatomic ion is the same as its oxidation state. So sodium is +1 and chlorine is -1. Okay, so that first one, it's kind of easy to tell that sodium is losing electrons and chlorine is gaining electrons. But it's a little less clear with B. So in B, we're not forming an ionic compound, so we have to rely on these oxidation states. So the oxidation state on hydrogen is +1, and there's 4 of them, so my total positive charge is +4. So because this is a neutral compound, carbon has to be -4. Here we have oxygen gas in its standard state. When oxygen is in a compound, its charge is -2, or rather its oxidation state is -2. So since carbon dioxide is a neutral molecule, there's 2 oxygens, the oxidation state of carbon has to be +4. In water, the oxygen's oxidation state is -2, and hydrogen is +1. Okay, so in my next one, we have PBS reacting with oxygen. So the oxygen will have oxidation state of 0, and PB and S are going to be monatomic ions. So the charge on sulfur and lead is going to be the same as the oxidation state. So sulfur is -2, then the lead has to be +2. Here we have PbO, so oxygen is -2, and lead then has to be +2. And then looking at SO2, so this needs to be -2 for oxygen, and then sulfur has to be +4 because this is a neutral molecule. Okay, the next one we're looking at is PbO plus CO. So oxygen is -2, so then the other ion must be +2. Lead solid would be 0, and for carbon dioxide, this would be +4 and -2. So the reason we want to assign these oxidation states is so that we can determine what's being oxidized and what's being reduced. So oxidation must always be paired with reduction. Oxidation is an increase in oxidation state caused by the loss of electrons, and reduction is a decrease in oxidation state due to the gain of electrons. So one of the things we talked about was Leo goes grr. So lose electrons oxidized, that means that the oxidation state is going to increase. And whenever we lose, gain electrons, we have reduction. That means that the oxidation state decreases. So we want to color code what's being oxidized and what's being reduced. So oxidized and reduced. So oxidized will be in yellow, and reduced will be in blue. Okay, so let's take a look at sodium and chlorine gas here. So sodium is going from 0 to +1, which means that it's being oxidized. So then my chlorine must be reduced. Okay, in the next one. So carbon goes from -4 to +4. So that's being oxidized. And then our oxygen then is going from 0 to -2 in both places here. So that is being reduced. For the next one, sulfur is going from -2 to +4. So that's going to be oxidized. And the oxygen is going from 0 to -2. So it's being reduced. In the next one, lead is going from +2 to 0, and carbon is going from +2 to 4. So carbon is being oxidized and my lead is being reduced. So now we want to go ahead and balance some reactions here. So this is a lot of steps, but once you get practice at it, you'll see it's not so bad. So we're going from oxidation state 0 to +2 here, and we're going from +1 to 0 here. So I want to go ahead and identify my oxidation and reduction. So my reduction is going to be going from H plus to H2. And I'm actually going to move that over so I have a little bit more room. Okay, so there's my reduction. We also have our oxidation. So our oxidation is going from Zn solid to Zn2 plus. So that's my oxidation. Okay, so the first thing that we want to do is balance atoms other than hydrogen and oxygen. So zinc is already balanced, so we're already done with that step. The next step is to take care of oxygen by adding water. We don't have any oxygen here to worry about. So then the next step is going to be adding H plus to make sure that's balanced. So I can go ahead and put a 2 in front of that guy, which is going to give me the correct number of H pluses on both sides. So now that we've taken care of all of those things, we need to deal with the number of electrons. So I'm going to total up the positive charge, the charges on both sides, and then I need to add electrons to balance that out. So on this side, the charge is +2, and on this side, the charge is 0. So I'm going to need 2 electrons to balance that out. For zinc, so my charge on this side is 0, and my charge on this side is +2. So I'm going to need 2 electrons here. So we want to make sure that the number of electrons that are produced during oxidation is the same as the ones that are consumed during reduction. So we've got 2 and 2 already here, so we're good there. And now I just need to combine these equations together. So I want to cancel out things that are the same on both sides. So my electrons will cancel. So I can go ahead and write my overall equation now. It's going to be 2H plus my solid zinc to form H2 gas and Zn2 plus. So that's our balanced equation. Okay, let's take a look at 4 here. So 4b rather. So here we need to assign some oxidation states. So that will be 0. That'll be +2, -1. Oxygen is -2, and there's 4 of them. So that gives me -8. And the charge is -1. So then Mn has to be +7. Okay, so now we can identify our oxidation and reduction. So MnO4 minus is going from +7 to +2. So that's going to be my reduction here. So my oxidation then is the chlorine. So the chlorine is going from -1 to 0. Okay, so first we want to balance things other than hydrogen and oxygen. So that means I need to put a 2 here. Then I want to take care of oxygen. So in my reduction equation here, I'm going to add 4 waters. This way I have 4 oxygens on both sides. So then the next thing we want to deal with is hydrogen. So I just added those 4 waters. So to balance out those hydrogens, I'm going to add 8 H pluses. Okay, so now I need to total up the charges on both sides. So this side will give me +7, and this side's going to give me +2. So that means that I'm going to need 5 electrons. That way both sides are +2. For chlorine, this side is -2 and this side is 0, so I need to put 2 electrons over here. So the number of electrons consumed must be the same as the number of electrons that are produced. I've got 5 and 2 here. So what I'm going to do is I'm going to multiply everything in my top equation by 2, and then my bottom equation I'm going to multiply by 5. That way we have 10 electrons on both sides. So I'm going to multiply this guy by 5. So this becomes a 10. This becomes 5. And this becomes 10. So my reduction, I'm going to need to double everything. So 5 electrons becomes 10. 8 hydrogens becomes 16. We need a 2 in front of that guy, a 2 here, and this becomes 8. Okay, so now that we have the same number of electrons on both sides, we can cancel and combine. So I can cancel out these 10 electrons, and there's nothing else for me to cancel out here. So I'm going to go ahead and combine this together into my balanced equation. And there's my balanced redox equation. Now the next one is a little bit different because we have a basic solution here. We also have only one reactant being made into 2 products. So let's go ahead and start by identifying some oxidation states. So that guy will be 0. Bromine is a liquid in its standard state. Oxygen is -2, and there's 3 of them. So bromine here has to be +5. And here we have just the ion bromine. So we need to identify our half reactions here. So they're actually both related to bromine. So Br2 becoming BrO3. So that is going to be my oxidation. We're going from 0 to +5. We also have our reduction going on here. So my reduction reaction is going to be Br2 into Br minus. So first I want to take care of things other than oxygen and hydrogen. So I'm going to put a 2 in front of this. And then I'm going to put a 2 in front of that guy. So now I need to take care of oxygen, and I've got 6 oxygens, so I'm going to add 6 waters. And no oxygen to worry about for the bottom one. Okay, so then what else? Now we need to handle those hydrogens we just added. So I'm going to put 12H plus here to handle the 6 waters that we added. So now I want to add up the charges on both sides. So this side is 0. This side is going to be +10. And for my reduction, I've got 0 and -2. So to balance this out, I'm going to need 10 electrons on this side. And then I'm going to need 2 electrons on this side. So I want to make sure that the number of electrons produced and consumed is the same. So I'm going to take my bottom equation and multiply that by 5. So this 2 electrons becomes 10, this becomes 5, and this becomes 10. So now I want to cancel out anything that is the same on both sides. So the electrons will cancel out, and that's about it. So now we can go ahead and combine these 2 equations together. So I'm going to combine my bromines, so I have 6 total. Okay, so here's what we get. Now this one is different because it's in basic solution. And all that it means is that H plus, that 12H plus, would get neutralized in solution. So you're just going to add enough hydroxide to both sides to neutralize that 12H pluses. So when you do that, the 12H pluses and the 12 hydroxides are going to neutralize, and we're going to get 12H2O. So now I can go ahead and cancel out some more water, because I have 6 here that I can cancel out, and 12 here becomes 6. So I can go ahead and just rewrite my equation to get our final answer here. So it's going to be 12OH minus plus 6Br2 to form our 2BrO3, our 10Br minus, and 6 water molecules. So there's our equation balanced in basic conditions. So in acidic and neutral conditions, we don't have to worry about that. Those H pluses can exist in solution. But under basic conditions, those H pluses are going to get neutralized. So what does it mean for a substance to be oxidized? So oxidized means that we are going to lose electrons. So the oxidation state is going to increase. So if you think about something reacting with oxygen gas, will be oxidized. So if we take something like so because oxygen is an element, right? We have O2 in its standard state. Its oxidation state is always going to be 0. So then over here, we see that oxygen has to be reduced because it's going from 0 to being in a compound. And in a compound, its oxidation state is -2. So that means then that my hydrogen, or my carbon rather, must be being oxidized because oxygen will always be reduced. If an element is a reactant or a product, a reaction must be oxidation-reduction. Why is this true? So if we go from a pure element in its standard state, its oxidation state is going to be 0. And then if we form any compound, then the oxidation state is no longer 0. So that compound is going to have different oxidation states than the pure elements. So we know that this is oxidation reduction because we have a change in the oxidation state. Okay, question 7. This equation appears to be balanced, but it's not. It's not balanced with respect to electrons. And a big hint to that is that you've got silver, which is +1, and copper, which is +2. So we're going to go ahead and split this into our half reactions and balance it just like we've been doing. So starting with my silver. Silver is going from +1 to 0. So that is our reduction. So then copper going from 0 to +2 is my oxidation. Okay, so this is already balanced with respect to atoms, but we need to balance it with respect to electrons. So I need 2 electrons over here, and then I'm going to need 1 electron for silver. Now I want to make sure that my number of electrons consumed and reduced is the same. So I'm going to double everything in my top equation. So now that I do that, those electrons are going to cancel out. And then when we write our final equation, we see that we have 2 silvers plus copper to form 2 solid silver and our Cu2+. So now this reaction is balanced with respect to atoms and electrons. So why do reactions have to be both atom balanced and electron balanced? So for electron balance, any electrons produced must be consumed. So these half reactions are paired. This oxidation and reduction are paired because one step makes electrons and the other step consumes electrons. So we have to make sure that the number of electrons consumed and produced is the same. And then atom balanced, of course, we have law of conservation of mass. The atoms we start with are the same as the atoms we end with. We've just rearranged them into something different.